let's see, I got two versions here that I'm hoping that either one of them will work.
Okay. We see it partially only. Okay.
Can you see the screen?
Yes.
Okay, excellent. So let me see.
So our next speaker is Berglund. He will tell us about machine learning, Kreuzer, Skarke Calabi manifolds. Please go ahead.
Okay, thank you. And thanks to the organizers for putting together this very nice workshop. And of course, we all had hoped to be in South Africa, like some of us were 2 years ago. But that will have to wait for another year. And I'm definitely an outsider to this field, although I've enjoyed being participant at some of these earlier meetings, in particular, going back to the Northeastern meeting 4 years ago. So I'm going to talk about a paper that I wrote with, somehow there was a spell checker that changed Vishnu's name to Jishnu. I apologize for that. So this is, of course, with Vishnu and my student Ben Campbell here at UNH. Ben is an undergraduate and he's finishing up this year. He's a senior applying to grad school. And he is the one who's been running the machine learning part. So he may be online here and could answer more detailed questions when we come to that. Oops. Okay, now of course I can't advance the screen. I should have checked that, of course, before. No, okay. Let's see. Let me escape. Oh, actually, there we go. Okay. Now it seems to be working. Excellent. So let me state the sort of the motivation and the results from the very beginning, in case people are having to run off for coffee or the usual kind of thing. So what we're doing is we're using machine learning to learn certain topological data from everyone's favorite Calabi database, that is the Kreuzer Skarke database. Well, it's one of the many databases. And what we find is that the neural network that we used was able to learn an exact expression for, in particular, well, for the Euler number of the Calabi. The Calabi is realized as a hypersurface in a toric variety from these reflexive polytopes. And it's able to learn that with just 4 pieces of data that I'll specify later that depend on the polytope and its dual. And now, of course, we also try to do the same thing for the H11, the individual Hodge numbers H11 and H21. However, there is a lower accuracy as far as what the neural network can learn. And so this is indicating that there's no such simple analytic expression in terms of these 4 pieces of data. And here is just a small cartoon of the simplest type of 2-dimensional reflexive polytope. To the left is the Newton polyhedron associated with the ambient space P2, and the polytope to the the polytope to the right is the so-called spanning polytope, from which one constructs the fan, triangulating giving the cones, etc. And that would then give you the actual toric variety, in this case, the complex projective space of dimension 2. Okay. So here's a quick outline. I've already gave you the motivation. I'll provide you some background and discuss the reflexive polytopes, and then the machine learning techniques, moving on to the numerical results that then points to this analytic formula. And then I finish with the summary and outlook. So just a little bit of a background. Of course, we've heard a lot about this already in this workshop. As we all know, there are these large data sets of string vacua. The idea being that among some of these vacua, in fact, it's already been established that there are phenomenologically viable constructions that lead to something that is at least semi-realistic as far as the particle physics. And some of those are the complete section Calabi-Yau. We'll go back to Candelas et al., as well as Green and Hübsch in the 80s. And then more specifically, what we're interested in is the work by Kreuzer and Skarke in the mid to late 90s, going into 2000, on constructing for 3 and 4 dimensions the complete classification of the reflexive polytopes. And then, of course, also this database provides you with the information about the Calabi hypersurface and computes, sort of automatically what the Euler number and the Hodge numbers are, given that you specify a particular polytope. Now, we're certainly not the first. Many people in the audience, including people here in the audience, have been using machine learning to study topological properties of Calabi manifolds. And what's interesting is that this is not just providing a way of sort of finding patterns and sort of numerically getting approximate results, but also actually finding exact results. Particular work by Berglund et al. From a couple of years ago, it showed how you can compute the cohomology classes of various line bundle in Calabi-Yaus, which of course is very interesting. Now, some of the earlier work on using these databases go back to the work by Berglund et al., and then that was refined by Urban and Finatello on the Calabi-Yaus realized as complete sections in 3 dimensions. So these are 3-dimensional Calabi-Yaus. So this is a smaller class of Calabi-Yaus of about 7,000 or so, but to very high accuracy, especially the work by Urban and Finatello, it's essentially close to 100% accuracy of calculating the Hodge numbers. And this has been extended to Calabi-Yaus, 4-dimensional Calabi-Yaus, also complete section Calabi-Yaus. Actually, I forgot this. The references here are somewhat sparse. There's also work by Urban and collaborators on the 4-dimensional case. And then very recently, in fact, we heard about this earlier this week, paper that came out, I believe, just yesterday by Berglund et al. On learning Calabi hypersurface in weighted projective spaces. This is one of the original classes from the late 80s, early 90s, which falls within the Kreuzer Skarke database as special cases. So once again, here are the motivation and results in case just you forgot about that. So this is what we find in our paper. So what just a very brief telegraphic review of what the Kreuzer Skarke database is and the reflexive polytopes. So first, the definition of the reflexive polytope is a convex hollow lattice of a lattice polytope with a single interior point. So these examples that I had on the motivation results page down in the corner here gives you the prototypical 2-dimensional case, of which there are 16 reflexive polytopes. So these pairs, or some of them are their own dual. I'll come to the definition of a dual polytope in a second. And then Kreuzer and Skarke classified the 4,319 reflexive polytopes in 3 dimensions, and this close to 500 million famous number in 4 dimensions. Just as a brief comment, in 5 dimensions, there's only a partial classification, and of course this is not just interesting from a mathematical point of view, but as we're interested in constructing Calabi fourfolds, elliptically fibered Calabi fourfolds for F-theory compactifications. Having that, knowing what that complete class is, would be interesting. And who knows, maybe this is something where one can apply machine learning to. So the work by Kreuzer and Skarke built on Batrev's mirror construction, and also Batrev and Borisov's work on generalizing this to F partitions that give you the complete intersection result in toric varieties. And the idea is that given a toric variety, X delta, then and here, that toric variety is is constructed by looking at a given triangulation of the dual polytope delta star, and then by mirror symmetry, there's another hypersurface in a W in a different toric variety X delta star, which is obtained by triangulating delta instead of delta star. So that gives you the ambient space, and then the defining equations are just these hypersurface equations where the equation over to the left is the one that defines the manifold M, and then the equation over to the right is the one that defines W. And xi here are the coordinates on the toric variety X delta, and yi are the coordinates on the X delta star, the sort of mirror ambient space. And vi star and vi are the vertices or the points in general in the dual polytope and polytope respectively. Now, what is the dual polytope? Well, the dual polytope is also a reflexive polytope, and essentially given by this inequality here, where you solve for by given any point in M, any given point M in delta, you then satisfy that inequality, and then you're looking once again at the convex hull. So that's, if you were to do this for this pair here, you start with the Newton polyhedron delta that's the polytope to the left, then you can construct delta star in this fashion. Okay, so now let's move on to the neural network. Now, so this is for me, very much a black box, and here's where Ben, my student, really came to the fore and implemented this neural network using these packages, Julia 1.6.2 and the Flux. So the basic idea is that this is starting with input data to the left. So this is a cartoon picture. You have the input data, and here I'm flashing this, and I'm going to talk more in detail about what that input data is to the left, and then it's forwarded in these 5 hidden layers, with each hidden layer having 300 neurons, and at the end of the day, it's then giving a prediction for what the different labels, depending on whether you're trying to train on the Euler number H11, H21, or H11 plus H21. And here, of course, H11 and H21 are the number of Kähler and complex structural deformations, respectively. Now, what is the input data? So L of delta is the number of points in the original reflexive polytope. So if we were to go back to this picture here of the polytope delta to the left, the number of points there in that polytope is, if we count those points, has 10 points in delta. So L of delta would be 10 in this case, and L of delta star would be 4. So those are the two input. Now, what is L of 2 delta and L2 delta star? Well, we scale up these polytopes. So I should have had, you essentially just multiply each of the vertices by a factor of 2, and then you count the number of points, and that gives you, and similarly you do that for delta star. Now L is rather 2 delta and 2 delta star. Those two polytopes, they are obviously not reflexive because they contain more than one interior point. But this gives information that turns out to be sufficient for this network to provide essentially, close to 100% accuracy. Well, in the high 90%, 96% accuracy on this randomly sampled selection of polytopes that we look at. Okay, so here are the numerical results. So what did we do? We we took up a random selection of data points. In fact, let me just go to, actually, do I not have that here? For some reason, no, that's right. So I did not include a plot. So these are randomly selected data points from the Kreuzer Skarke database, 1 million of those data points. And we then performed this experiment where in this class of models, we would train on 80% and then test on 20%. And the training and testing sets, we would do this 100 times, choosing a different randomly selected 80% of polytopes from that 1 million initially randomly selected reflexive polytopes. And here are the accuracies. So the label to the left, this is chi, H11, H21, and the sum. As you can see, the accuracy is in the high 90%, 97%. The plus minus here is the standard deviation for this experiment of having run this 100 times. The absolute error is very low, and similarly the relative absolute errors. Now, when it comes to H11 and H21, it's close to 50%. So it certainly could be better, but it's not that bad. And then H11 plus H21 is not as good. And so this is indicating that the network is able to obviously learn chi very well, the Euler number, and then and also the individual Hodge numbers. But then when it comes to the sum, that's certainly quite a bit worse. Then the experiment was repeated by, instead of just randomly selecting from the 500 million reflexive polytopes, we instead chose polytopes along the boundary. And I don't know what happened to I had this in a previous incarnation of this talk. There's in the standard plot of all the Hodge data, we have the Hodge data there on the boundary. So this is for, essentially where H11, either H11 or H21 are very large. And so we just wanted to make sure that there wasn't a sort of a bias towards the center of this famous Hodge data plot, in which is the one that's mostly densely populated by the 500 million reflexive polytopes. And so we wanted to see, to what extent we could learn, or the network that we used also was able to predict the topological data for the boundary. And this here is representing what's happening when you train and test on the boundary data. And this is the same experiment that we did, where you pick 80% of those 1 million reflexive polytopes along the boundary, and you test on 20, and then you repeat that by randomly selecting 80% in each time. And so the accuracy is for the Euler number is about the same. And then for H11 and H21 is actually quite a bit better. Instead of being about 50%, it's of the order of 75%. But still, obviously, not quite, at the level of where we could say for sure that okay, we would expect an analytic expression for this. Well, even in the case of chi here, the result by itself is not indicating this. Okay, so now here is just to show the confusion matrix, where you're essentially just plotting for a particular choice of this in the randomly sampled data set, and similarly for a particular choice of the boundary data. So here, this is just one of the 100 experiments. And in fact, for this particular one to the left, for the randomly sampled, the accuracy is almost 100%, 99.25%, with a small absolute error, mean absolute error, and then the accuracy is for the boundary data is not quite as good, but 96% is still quite good. And so you can see here that the points essentially congregate along the diagonal as expected, based on how well how good the accuracy is. Now, what we then did was to, based on the fact that we were able to get such a high accuracy, especially for the Euler number, we did a linear regression using Mathematica. So so similarly to what was done in the case of the 1 million randomly selected points, we took a slightly smaller set out of that, about 200,000 reflexive polytopes and their duals. And then now an experiment was done similarly to what was done. We selected out of that set of 200,000 polytopes, 100,000 polytopes and their duals, and then repeated this linear regression, 100 times and the data here is the data that I provided here earlier, in terms of the number of points of the polytope, the number of points of the dual polytope, and then similarly for the scale, the twice scaled up polytopes and its dual. So, and then, with this linear regression, there will be a constant term, and then there will be in principle constant term, and then coefficients in front of the four input data. And then when you look at the accuracy by rounding to the nearest integer, you find that, well, it's sort of in the 50%. So that's but increases by quite a bit if you also allow for sort of a mistake of ±1. But clearly this is not something that you're going to say, okay, claim that here is an exact formula for predicting what the Hodge numbers are.
You have 5 minutes.
But then this is, say it again.
You have 5 minutes left.
5 minutes, excellent, very good. So now here's the interesting thing. So if we do now the same thing for the sum and the difference, well, the sum, not surprisingly, is as expected on what had been done for the machine learning analysis. The accuracy is quite low, 23%, and then increasing by another 38% if you allow for a mistake by ±1. Now, on the other hand, here is the amazing and beautiful result that expresses, well, the Euler number, or half the Euler number, as this particular linear combination with coefficients 9 and 1, or plus minus 9 and plus minus 1 for the 4 different data points. So when we came across this result, we said, okay, this is how come we haven't known about this? We've been looking at and computed Hodge numbers and Euler numbers in particular for this Kreuzer Skarke database for decades, literally. So how can we understand this? So, well, there are different ways in which one can think about this, and in some ongoing and soon to be published or appearing on the archive work with Tristan Hübsch, we essentially rely on this result going back to Butler and Schaller from 2016-17, where they obtained this combinatorial expression for the data of the polytope. So the data of the polytope here is given by the degree of the polytope and the degree of the particular phases, and the degree is essentially given by the volume of that phase, or the volume of the polytope. And the psi i's can also be they have two interpretations, and the interpretation that we're going to use here is that they encode information about also the polytope and the scaled up polytope, as we'll see in the next slide. But they also, and this is the original Lipgober-Wood identity from 1990, which it's an expression that tells you how the Hodge numbers are related to various types of Chern classes on the ambient space. But I'm not going to go into that detail now. So instead, the important fact is that there exists this notion of the Ehrhart series, or actually Poincaré series or Hilbert series, in which you have kind of a generating function in terms of this one parameter family T, where the coefficients are these number of points in the various scaled up polytopes. So it's an infinite series, but it can be rewritten using the fact that there's a geometric series that you can sum, and then you have a polynomial in the numerator. And the coefficients of that polynomial in the numerator are those psi I. And so then you just, by comparing these two expressions, you can read off what the psi i's are. Now, this is actually something that most of you may be familiar with if you look at a lower dimensional case. So for n equal to 2, then there's this famous 12 theorem. So in fact, you can go back and check that in this case, 12 is equal to the dimension of the polytope and its dual. And so in this example here, we had that the dimension of the polytope being the volume is 9 for the Newton polyhedron to the left and 3 for its dual on the right. So 9 plus 3 is 12, and that can be explicitly checked for, of course, all the 16 reflexive polytopes. Now in n equal to 3, there's something called the 24 theorem, which is the statement that essentially that the Euler number of the manifold is 24. And that takes this form here. Now, what about the really interesting thing? Well, so if you take this formula that was on the previous slide here now, and you put in that n equal to 4, and you work out what the various terms are, then you get this equation on the top. So of course, this is something that Butler and Schaller did, but then they also wrote down what the expression was for the dual polytope. But surprisingly, they actually then never did the natural thing. They took the sum of it because they were interested in something that was like a 24 theorem or 12 theorem, but they didn't consider the difference. So now, if you take the difference of these two expressions, you get, well, on the right-hand side, you get this difference of these different sums, and then you use the properties of reflexive polytopes that a particular phase is dual of a dimension. In this case, 2 is dual to a phase of dimension 1, and vice versa. And then you can rewrite those two sums on the right-hand side there as this as those two sums now in terms of, and here once again there is no, that's right, this is correct. And once you look at that, then you remember from Butler's original paper, in fact, an expression for the Euler number that's exactly this difference of those sums of products of the degrees of the phases and the dual. And that then allows you to write down an expression for the Euler number, which is the last equation, that nicely expresses this in terms of the number of points of the polytope and dual polytope and the degree of the polytope. Well, going back to Danilov, in his beautiful review from 1977, you can work out what the degree is in terms of the number of points and the scaled up points. And if you plug that in to this previous equation, you get that the Euler number is exactly what was calculated using the linear regression. Just as everyone's favorite example, just to show how sort of beautiful this is, if you take that the quintic hypersurface in P4, then of course we all know that there are 126 degree 5 monomials. That corresponds to the number of global sections. So that's L of delta. And then for the dual, there are 6. That's the mirror, essentially. The fact that the Fermat plus its unique mirror complex structure deformation, there are 6 of those terms. And then you have to do a little bit of work to get the scaled up versions. So 1001 and 21, respectively. You plug this into the formula, and lo and behold, you get that the Euler number is minus 200. Certainly before this, the last line, of course, is very well known, but I'd never thought of being able to compute this in this fashion. So I'm essentially out of time. So what we've been able to do is we find this beautiful result that expresses the Euler number, and sort of inspired by machine learning in terms of this very basic set of data from a particular reflexive polytope and its polar or dual. I'm going to skip this comment about computing H11 and H21. So now, of course, it would be interesting to see, can we possibly extend this, let's say, to 5 dimensions? Can we learn something about elliptically fibered Calabi in this fashion? And also, is it possible to generalize this to more general polytopes and other more generalized constructions like the GCCs in order to learn more about what machine learning can teach us about these data sets. So thank you very much.
Thank you, Per, for the very nice talk. Do we have questions? We have one question from Andre.
Hi, Per. Thanks very much.
Hi, Andre.
I was wondering, there are sort of formula for H11 and H21 due to Batiev, as far as I remember.
Yep.
In terms of toric data.
Yeah, exactly.
I mean, couldn't you use those as some kind of inspiration of what you feed your neural network? I mean, it seems to me that for the Hodge numbers, these 4 values that you fed into it, maybe they're just not enough to encode the information.
That's right. No, so exactly. So I'm glad that you. This was obviously a planted question because I didn't cover the last line here in the previous slide. So indeed, so there are, as you're possibly aware or most likely aware of, there are the special polytopes for which, in particular in the case of H11 and then by mirror symmetry H21, where there are these very simple expressions just given in terms of the number of points in the dual polytope and then subtract by 5. So these are what people refer to as favorable situations. So where all of the Kähler classes are inherited from the ambient space. Yeah. So indeed, these are the first 2 terms in Batiev's exact expression. So there are sort of the correction terms which would say that, well, if you have interior points in the facets, then you have to subtract that. And so that's saying that not all of the toric divisors are going to contribute to the to H11, and similarly then for mirror symmetry. And then of course there are these non-toric contributions as well, which is a further term. And then similarly by the H21. Yes. So exactly. We know of course that there is an exact expression, but that exact expression, you then need to know more detailed information about, what the vertices are, and so on and so forth, as far as it's essentially, knowing things like these particular but more complicated expressions in terms of the products of the degrees of a phase and a dual phase. And so it would, of course, be very nice if there was a way in which we could provide just maybe one additional input data to also then nail down what H11 and H21 would be. Thanks. Yep.
Okay, next. Fabian had a question?
What's the same question?
Okay. Okay, so if there are no more questions, let's thank here again.
Sorry, can I just ask a quick?
Oh, hey, David. Yes.
Hi. Sorry. Yeah. No, I was just thinking about this. I may have missed it, but you're sampling the whole Kreuzer Skarke set, right?
That's right. That's right. So these were these missing plots that should have been on this slide here. So in fact in the paper, if I were to click on this here, then we are taken to the paper, and then in that paper, you can still see the screen, I assume, right? I'm scrolling through the paper here, and
no, the screen is blank.
Black, I'm afraid.
Oh, resume share. Okay, sorry. Okay, resume share. Okay, sorry. So if you go to the paper, in the paper, so indeed, if you look at the plot there, then they're indeed sampled from the whole data set for this first result here. So but because of the distribution and frequency of reflexive polytope that's sort of clustered in the center, that those 1 million data reflexive polytopes mainly come from the sort of the bulk of this the Hodge data plot.
I was going to ask, because we found, which of course is a tiny sample compared to what you did, that when you had the sort of extrema, it sort of seemed to split up more and was not evenly distributed, and that there was some like, but that was only for large H21 and H11. They seem to behave very different to the ones that were the majority of them. And I was just wondering about whether you had any sort of notion about when you were sampling, whether you were trying to get what the majority did, or whether you were going to be sensitive to interesting structures that might be at the extrema.
That's right. That's right. So indeed, so that's why we did this second sampling from the boundary. So there, we then took essentially what you're saying. A part of that boundary is out at the corners where you have either then a large H11 or large H21, and so that's where, in fact, the predictions and the accuracy for H11 and H21 go up.
Yeah, exactly. Yeah.
And so that's right. So those types of polytopes then have this property that the H11 is coming essentially only from the ambient space, and then by being symmetry, right? So these correction terms that are there in Batra's exact expressions, which require you to know detailed information about how many points there are in the facets, and also these non-toric contributions where you need to know things about interior points and their dual in lower dimensional faces. Those are mainly absent for those large values of H11 and H21. Yep.
That's very good. Thank you.
It's something similar in your situation. If you now were to sort of look at, well, you can think of the weighted projective space as some Landau-Ginzburg type orbifold, and I would guess then that in particular these the twisted sector contributions then will be largely absent, and you will just have contributions that are sort of just from the toric part, sort of where you resolve the singularities, but not the non-toric part of the.
Okay, that's very useful. Thank you very much.
Yep. Welcome.
Okay, more questions? If not, then let's thank Per again, and we should reconvene at 6 p.m.